Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 is a multi-step question, and it is to calculate the number of atoms in the universe. The following steps will guide you through this calculation. Okay, so let's do this step by step. Part A. Planets constitute less than 1% of the total mass of the universe and can therefore be neglected. Stars make up most of the visible mass of the universe, so we need to determine how many atoms are in a star. Stars are primarily composed of hydrogen atoms, and our Sun is an average-sized star. So calculate the number of hydrogen atoms in our Sun, given that the radius of the Sun is 7 times 10 to the 8 meters, and its density is 1.4 grams per centimeter cubed. The volume of a sphere is given by volume is equal to 4 over 3 pi r cubed. So hint, use the volume and the density to get the mass of the Sun. Okay, so very helpful information. So for part A, first let's calculate the volume. So volume is equal to 4 over 3 times pi r cubed. So they tell us the radius of the Sun, which is 7 times 10 to the 8 meters. So let's plug that into our equation for volume. And if we plug this into like a calculator, you end up with a volume of around 1.44 times 10 to the 27 centimeter cubed. Okay, so now for part 2 of part A, I guess, is to calculate the mass of the Sun. And to do that, we would use the density equation. So density is mass over volume. And we want to calculate for mass. So we do mass is equal to density times volume. And the density is 1.4 grams per centimeter cubed. And the volume is what we found in the previous step. So 1.44 times 10 to the 27 centimeter cubed. Okay, so if we multiply these two values together, we get a mass which is 2.016 times 10 to the 27 grams. And this is the mass of hydrogen atoms in the Sun. Okay. So we know the mass of the hydrogen atoms in the Sun. Now let's try to figure out how many atoms this is. How many atoms of hydrogen are in the Sun. So in order to find the atoms, we first need to find the number of moles. So the number of moles is equal to mass over molar mass. The mass of hydrogen atoms was the 2.016 times 10 to the 27 grams. And the molar mass of hydrogen is 1.01 grams per mole. So now this gives us the number of moles of hydrogen in the sun, which is 1.996 times 10 to the 27, I think my notes says. Moles. And now that we have our answer in moles, we can convert to atoms by using Avogadro's number. So if we multiply by Avogadro's number, which is 6.022 times 10 to the 23, and this is atoms per mole, we can get the number of atoms in the sun. So we end up with 1.2 times 10 to the 51 atoms in the sun. Okay, so part 2, or part B, the average galaxy, like our own Milky Way galaxy, contains 1 times 10 to the 11 stars, and the universe contains 1 times 10 to the 9 galaxies. Calculate the number of atoms in an average galaxy, and finally the number of atoms in the entire universe. Alright, a lot of big numbers that are about to occur. This is part B. And first we need to find the number of, or let me try to find the number of hydrogen atoms per galaxy. Okay, so first we need to multiply the number of atoms in one star times the number of stars. So back to our previous step, we calculated the number of hydrogen atoms in one star to be 1.2 times 10 to the 51. So I'm going to say H atoms per star. So now I just need to multiply this by the number of stars in a galaxy. So we have 1 times 10 to the 11. And then this is going to be stars over galaxy. So now we can get the number of hydrogen atoms in the galaxy. And this is going to be 1.2 times 10 to the 62 atoms per galaxy. Okay, so now we need to find how many atoms in the universe. So hydrogen atoms per universe, we need to multiply again. So now we have 1.2 times 10 to the 62 H atoms per galaxy And now we need to multiply by 1 times 10 to the 9. And this is galaxy or galaxies per universe. So now our unit for galaxies, I guess, will cancel out. And if we multiply the two, we have 1.2 times 10 to the 71 atoms per universe, which is a lot. So now let's look at part C. You can hold 1 times 10 to the 23 atoms in your hand. 5 copper pennies constitute 1.4 times 10 to the 23 copper atoms. How does this number compare with the number of atoms in the universe? Well, let's say there was the 1.2 times 10 to the 71 atoms per universe. Let's divide this by 1 times 10 to the 23 atoms that can fit in your hand. And you still get like a pretty high number. Maybe 1.2 times 10 to the 48 more atoms. It's a pretty large number to compare, therefore relatively large. Okay, so pretty long multi-step question, but we figured out how many atoms are in the universe. Let's compare our answer with the junior tutors. For part A, given the radius and density of the sun, we can calculate the number of hydrogen atoms in the sun as follows. First, we should get the volume of the sun, which is a sphere, by using the given radius and the formula for volume. So they got... Okay, I think they accidentally put the radius as 7 times 10 to the 10 instead of 10 to the 8. So their answer will be off by like a couple exponents in the end. But the work was correct. But they still ended up getting a 1.4, but their exponent is 10 to the 33. So we can just take note of that later on. The mass of the hydrogen in the sun can then be calculated by using density. So mass is density times volume, and they got 2.0, again, times 10 to the 33 is incorrect. Okay, so now they calculated for number of atoms. So the 6.23. So the units for Avogadro's number is not atoms per gram, it is atoms per mole. So they're just missing the step of when we need to calculate for number of moles. So again, number of moles is equal to mass over molar mass. So they're just missing that one step. But you can see that even though they forgot this step, by dividing by the molar mass of hydrogen, which is pretty much just 1, they get a similar value. But even then, it's a bit off because of the exponent. But still, I'll take note of that as well. So then for part B, they calculate the number of hydrogen atoms in one galaxy. So they multiplied 1.2 times 10 to the 57 in their case, times 1 times 10 to the 11 to get the number of atoms in a galaxy. And then they solved for the number of atoms in the universe. So then you multiply that value by 1 times 10 to the 9. And they got 1.2 times 10 to the 77. So again, it's pretty close. The only reason why it's a bit off with the exponents is because they inputted the wrong radius at the very beginning. C, the number of atoms that can be held in the hand, is almost incomparable to the number of atoms in the universe. Number of atoms in the universe is relatively larger than that we can hold in our hands. So that is correct. So I'll say most of the steps in the solution are correct. However, A in the initial calculation for solving for volume, the radius should be 1 times 10 to the 8 meters. And then B, before we multiply by Avogadro's number, which is 6.022 times 10 to the power of 23 atoms per mole, we need to calculate number of moles for hydrogen by using N is equal to mass over molar mass. The final answer should be 1.2 times 10 to the power of 71 atoms in the universe. Okay, so just some minor mistakes, but I think it's important to note that for Avogadro's number, the units aren't in grams per mole. Well, it's not grams per atoms, it's number of moles per atoms. So that's important to note as well. Or atoms per mole, sorry. But yeah, I can see how it can get pretty confusing. Okay, so question number 2. Is boron trihydride polar or nonpolar? So first, let's find the Lewis structure of Bh3. So when we write the Lewis structure, we first need to find out the total valence electrons for this molecule. So boron has 3 valence electrons, and hydrogen has 1. And there are 3 hydrogen atoms in Bh3, so we multiply that and get a total of 6 valence electrons. So when we write out the Lewis structure, we write boron in the middle as our central atom. And then I'm just going to write out all my hydrogens that have a single bond to the boron. Now let's count out how many electrons I've drawn so far. So if we count out 2 electrons in each bond, we have our 6 electrons already. So note that boron doesn't have 8 electrons, and this is important because boron can be an exception to the octet rule. So it's perfectly satisfied only having 6 shared electrons. So this is our Lewis structure. And now we need to find out whether or not Bh3 is polar or nonpolar. So first let's examine the boron-hydrogen bond, since this molecule is only composed of the boron-hydrogen bond. So we need to see if this bond is polar or nonpolar. And when we try to figure out if a bond is polar or nonpolar, we want to look at their electronegativity differences. So let me look up electronegativity values on the periodic table. So boron's electronegativity is 2 and hydrogen's is 2.1. So they're pretty close in electronegativity values, and the difference is only 0.1. So because it's only 0.1, then this tells us that the boron-hydrogen bond is nonpolar. So now let's look at the molecule as a whole. So not only does it contain nonpolar bonds, so it only contains nonpolar bonds, but we can also see that the molecule is symmetrical. So even if there was a slight pull of electronegativity, because Bh3 is symmetrical, all these, well, not really dipole moments could cancel each other out. So we also have a nonpolar molecule. This is because it's symmetrical and because the bonds are nonpolar as well. So let's see what the junior tutor said. Polarity refers to the charge separation which causes the presence of dipole moment. Additionally, polarity can be viewed from the perspective of a bond or the entire molecule itself. A bond can be polar because the electrons are unequally shared between the bonded atoms due to their electronegativity difference. However, although a molecule has polar bonds, this does not imply that the entire molecule is polar. If the molecule symmetry results in the cancellation of the dipole moments overall, the molecule becomes nonpolar. To determine if Bh3 is polar or not, let us first check if it contains polar bonds. Electronegativity difference between boron and hydrogen is only 0.16. Many references, bonds are classified as polar if the difference is between 0.4 to 1.7. So even that, usually it can also be 0.5 to 1.69. So a lot of references say different things. But below this, bonds are said to be nonpolar. Based on this, the BH bonds are all nonpolar, so the entire molecule is nonpolar as well. Yep, so this solution is correct. Okay, so question number 3. Answer the following questions about the molecule dichlorine oxide. How many valence electrons does it contain? So first, let's calculate the total number of valence electrons. So to do that, we see that chlorine has 7 valence electrons, and there are 2 chlorines. So we multiply this by 2. Oxygen has 6 valence electrons. So 14 plus 6 is 20. Part B, draw a valid Lewis structure. So let's draw our oxygen in the middle. And then we'll draw single bonds to chlorine. Now let's see how many electrons I've drawn so far. Once I finish in drawing all the lone pairs on chlorine, if we count it all out, each bond contains 2 electrons. So far I've only drawn 16 electrons, so I need 4 more since I have 20 in total. So I'm going to draw the other 2 as lone pairs on the oxygen. So now we have a valid Lewis structure. Part C, label all polar bonds. So typically you have a polar bond when the electronegativity difference between the 2 atoms is greater than 0.4. So I'm going to say greater than or equal to 0.5, but less than 1.69. So now let's calculate the electronegativity difference of an oxygen and chlorine bond. So let's find their electronegativities on here, and we'll see oxygen is 3.5 and chlorine is 3.0. So the difference is 0.5. So therefore we have a polar bond. And now, what is the shape around the central oxygen atom? Okay, so let's look at our central oxygen atom. There are 2 lone pairs, and there are 2 bonded atoms. So let's look at the shape by using the Vesper theory. So this is a handy table that can tell us the type of molecular shape and the electron geometry, the hybridization, and the bond angles of a certain molecule. So for this molecule in particular, oxygen has 2 lone pairs, so 2, and 2 bonded atoms. So we have this configuration right here. So therefore the molecular shape is bent. And we have a tetrahedral electron geometry. So now, question E, let's try to fit it on the side here. Is Cl2 Oh a polar molecule? Explain. Well, because of the bent shape of the molecule, and because oxygen is a bit more electronegative than the chlorine, then there is an uneven pull of electrons. So I'm going to say that Cl2 Oh is polar since molecule is bent and any dipole moments that are formed aren't cancelled out. Okay, so the junior tutor said that oxygen belongs to group 16, so it has 6 valence electrons, and chlorine belongs to group 17, therefore it has 7. And then they calculated their total valence electrons to be 20. Yep. And when they drew out their Lewis structure, they got the same structure as well. And also calculated the formal charge for both of them, which is 0, so that's good. For part C, the covalent bond between the atoms is polar if the electronegativity difference between them is greater than 0.4 on Pauling's scale of electronegativity. The two bonds that exist are polar because the electronegativity difference between chlorine and oxygen is greater than 0.4. Yeah, it's a bit greater, 0.5. And then for D, the number of electron groups around an atom in a molecule is equal to the number of lone pairs on the atom plus the number of bond pairs around the atom. From the Lewis structure, we see the central oxygen has 4 electron groups, and out of the 4, 2 are lone pairs. Using the following table, made from the principles of the Vesper theory, we can conclude that the shape is bent or V. So it's right here. The covalent bonds become polar because of the electronegativity difference between the elements involved. Electronegativity difference causes the electrons in the bond to be unequally shared. This results in a partial positive charge on the less electronegative element and a partial negative charge on the more electronegative element. Charge separation with the partial positive charge and the partial negative charge of the other generates a dipole moment, which is a vector quantity. Okay, so they said that the molecule is polar, so this solution is correct. I'm going to note that oxygen is more electronegative than chlorine, so the dipole moments will point in the direction of oxygen. Okay, so question number 4 is to draw the Lewis structure of carbonyl fluoride, COF2. What are the electron pair geometry and molecular geometry around the central atom? What is the hybridization? And what orbitals overlap to form the sigma and pi bonds between carbon and oxygen? Okay, so let's find the total number of valence electrons in order to help us draw our Lewis structure. So carbon has 4 valence electrons, oxygen has 6, and fluorine has 7. And there are 2 fluorine atoms, so we multiply this by 2 and add them all up, and we get 24 valence electrons. So now over here on the right, I'll draw my carbon as my central atom. And then let's see what happens if I have a single bond with all of my terminal atoms. And then I'll just add all the lone pairs as I go. Okay, so let's recall that each bond contains 2 electrons. So if I were to count out how many electrons I've drawn so far, I have the 24, which is what I am looking for. But if we look at the carbon, it doesn't have a full octet. So the only element it can form a double bond with at this moment is the oxygen. I'm going to bring one of the lone pairs down to form a double bond with the carbon. And now everything is neutral, and we still have 24 electrons in the structure. So this is the correct Lewis structure. So now when we want to find the electron and the molecular geometry around the central atom, we first need to count out how many lone pairs and how many bonded atoms there are with the carbon. So the carbon has 0 lone pairs, and it has 3 bonded atoms. So the 2 fluorines and an oxygen. So now we would use our VSEPR table to find out the type of electron pair geometry and molecular geometry of the molecule. So when we have 0 lone pairs and 3 bonded atoms, we have both a trigonal planar molecular shape and a trigonal planar electron geometry. So therefore, trigonal planar for both. And we can see that the type of hybridization is sp2. So we have this answered, we have the hybridization answered, and now what orbitals overlap to form sigma and pi bonds between carbon and oxygen? So now when we have the pi bonds, this is when the p orbital of carbon I'm going to say 2p overlaps with the p orbital of oxygen to form the pi bond. And for the sigma bond, the carbon sp2 orbital and the oxygen sp2 orbital are used to form the sigma bond. Okay, so now let's see what the junior tutor said. So here's the Lewis structure for carbonyl fluoride. So it is the same as mine. Everything is neutral, and there are 24 electrons in the structure. The electron pair geometry around the central carbon atom is trigonal planar even if there are 4 bonding pairs around it, because the bonding pairs in the double bond are counted as one pair. The molecular geometry is also trigonal planar since there are 3 atoms and no lone pairs around the central atom. Carbon atom is sp2 hybridized, and one sp2 orbital of carbon overlaps with another sp2 orbital of oxygen to form a sigma bond. The unhybridized p orbital of carbon overlaps with another unhybridized orbital of oxygen to form a pi bond, hence the double bond. The remaining two sp2 orbitals of carbon form sigma bonds with the two atoms of fluorine, while the remaining sp2 orbitals of oxygen contain lone pairs. Yep. So the solution is correct. Okay, so question number 5. Is bromine trifluoride polar or nonpolar? So first let's write out its Lewis structure. That'll help us answer the question. So we need to find the total valence electrons of the molecule. So bromine has 7 valence electrons, and there are 3 bromine atoms. And for fluorine, there are also 7 valence electrons. So if we add this up, we get 28. Okay, so now let's draw fluorine as our central atom. Oh, sorry, it should be Br(F3). And then let me just switch these two. Okay. So bromine is our central atom. And fluorine are, the 3 fluorines are the terminal atoms. And now let's draw out all of the lone pairs on the fluorines and count out to see how many electrons I've drawn so far. So each bond contains 2 electrons, and there are 3 bonds, and then each fluorine contains 6 electrons as the lone pairs. So far I've only drawn 24 electrons, and I need 28. So I'm going to add another 2 on my bromine atom. And now we kind of have this kind of shape. Kind of messy, so I'm just going to not circle them. But yeah, so this is a valid Lewis structure for bromine trifluoride. So now we just have to find out whether or not this molecule is polar. So first let's see the polarity of a bromine and fluorine bond. So let's calculate the electronegativity difference of bromine and fluorine. So let's find their values on this electronegativity periodic table. So bromine is 2.8, fluorine is 4. So what is this, like 1.2? Yeah. So their electronegativity difference is 1.2. So therefore this is a polar bond. And this is because the difference in electronegativity is greater than 0.5, and it's less than 1.67. So therefore, all the bonds are polar, and the fluorines are much more electronegative than the bromines. So there's going to be dipole moments throughout the molecule, and the shape with the lone pairs allows these dipole moments to not be cancelled out. So therefore, the entire molecule is also polar. And this is because dipole moments are not cancelled out. So let's see what the junior tutor said. Polarity refers to the charge separation which causes the presence of dipole moment. Additionally, polarity can be viewed from the perspective of a bond or the entire molecule itself. A bond can be polar because the electrons are unequally shared between the bonded atoms due to their electronegativity difference. However, although a molecule has polar bonds, this does not imply that the entire molecule is polar. If the molecule symmetry results in the cancellation of the dipole moments overall, the molecule becomes nonpolar. So they found that the bond of bromine and fluorine is polar because of their electronegativity difference. And then they looked at the shape of the molecule. So it is T-shaped. So since fluorine is the more electronegative atom, the dipole moment of each bond points towards fluorine. Due to this shape, the dipole moments pointing upward and downward cancel each other out, but the dipole moment pointing rightward does not have any counterpart that cancels it out. Therefore, it is a polar molecule, assuming this orientation. Yep, so this solution is correct. Okay, so question 6. What is the name of this ionic compound? So when we have an ionic compound, this goes by a different set of rules compared to if we had a binary covalent compound. So when we name ionic compounds, we name the cation first, which is the metal, and then we name the anion, which is the nonmetal, or it can be, or these can both be polyatomic ions, in which case you would just name the ions. But in our case, we just have magnesium and nitrogen. And then if it applies, we would also state the oxidation state of our metal. I'm gonna also add, can also specify oxidation state. Okay, so now let's look at our compound. We have a magnesium cation, which has a 2+ charge, and we also have a nitride ion, which has a 3- charge. So therefore, the name of this compound is magnesium nitride. Okay, so let's see what the junior tutor said. The steps below outline how to name an ionic compound. Step 1. Identify the cation. If it's monoatomic, determine if it can have definite charge or multiple charges. Metals that can have multiple charges are usually from the D block, so any of the transition metals. If it can only have one charge, name the metal as it is. For example, magnesium is Mg. If it can have more than one charge, determine its charge, then name the metal as it is, followed by its charge, written as a Roman numeral in parentheses. Or you can use like the Greek name, but it's easier to just see the parentheses. And if the cation is polyatomic, composed of more than one atom, determine the name of the polyatomic cation itself. But in our case, it's just magnesium, so we're good. And then step 2 is to identify the anion. It's monoatomic, take its base name and apply an "ide" to its name. So for example, chlorine were the anion, then it should be named chloride. If sulfur were the anion, it should name sulfide. Let me just add this to my rules. You can add "ide" as the suffix. If the anion is polyatomic, determine the name of the polyatomic anion itself. So we just have the nitrogen. Last step is to put together the names of the cation and the anion. So for example, NaCl, sodium chloride, and MgSO4, magnesium sulfate. Using these steps, let us name the cation will simply be named as magnesium. The anion will be referred to as nitride. Together, the name of the entire compound is magnesium nitride. Okay, so this solution is correct. Question 7. What is the Lewis structure of PF6 minus? So first, let's find the total valence electrons of this ion. We have a phosphorus, which has 5 valence electrons, and we have fluorine, which has 7, and we multiply this by 6 since there are 6 fluorine atoms. And then the ion has a -1 charge, so I'm going to add an additional electron as well to the count. And we get a total of 48 electrons. So now, when we draw the Lewis structure, I'm going to draw my phosphorus as the central atom, and then single bonded fluorines just symmetrically all around. And now let's add in all of their lone pairs. Okay, so now let's count out how many electrons I've drawn so far. So if we see that each bond contains 2 electrons, and we have 6 bonds, that's 12, and then we just add up all of the lone pairs, so we have a total of 48 electrons. So now let's try to figure out the formal charges to see where that negative charge goes. So the equation for formal charge is the number of valence electrons minus the number of non-bonding electrons. So these are all the electrons in the lone pairs, minus the number of bonding electrons divided by 2. So in the case of the fluorine, let's calculate fluorine's formal charge. So all of them are the same, and they all have 7 valence electrons. The number of non-bonding electrons which are the lone pairs, is 6. And then each of them have a single bond, so there are 2 electrons in each bond. So 2 bonding electrons divided by 2. So 7 minus 6 minus 1 is just 0. And in the case of the phosphorus, phosphorus has 5 valence electrons. There are 0 non-bonding electrons because there are no lone pairs. And the number of bonding electrons, so we have 12 bonding electrons since there are 6 bonds. So 5 minus 6 is -1. So now we know that the negative charge will go on our phosphorus. So now let's see what the junior tutor said. First, to calculate the valence electrons, they got 48. They have the skeletal structure, filled out all of the lone pairs, and then calculated for the formal charge. Yep, so this solution is correct. Okay, so question number 8. What is the name of the compound Na2CO3? Okay, so let's break it apart into its separate ions. Na is the sodium ion, and CO3 is a polyatomic ion known as carbonate, CO3 2-. So if we put the names of the ions together, we get sodium carbonate. So the junior tutor said has metallic sodium and non-metallic carbon and oxygen atoms, which is our polyatomic ion. Name the metal, so we name the sodium. Step 2, find the ions in the compound. So this gives us the anion carbonate. And then they also have the helpful chart of showing all the different polyatomic ions you could have. So once they located it on the chart, then we can finally name it as sodium carbonate. So this solution is correct. Okay, so one last quick question. Draw the Lewis structure for Ch4O, in which oxygen is bonded to 2 kinds of atoms. Do not consider cyclic ring structures. That's helpful. So first, let's find the total number of valence electrons for this molecule. Carbon has 4, and hydrogen has 1. And there are 4 hydrogens, so we multiply this by 4. And oxygen contains 6. So if we were to add these up, we get a total number of 14 valence electrons. So first, let's draw my carbon, and I'll have it single bonded to 3 of the hydrogens, and another single bond to the oxygen so that it has a full octet. And now the oxygen will also have a single bond to the last hydrogen. So if we count out how many electrons I've drawn so far, each bond contains 2 bonding electrons, and we have 5 bonds in total, so I only have 10 bonding electrons out of the 14 that I need for the entire molecule. So for the last 2 electrons, I can put them as lone pairs on my oxygen, since both carbon and hydrogen are satisfied already. Hydrogen can only form single bonds, and it can't have any lone pairs since it only has 1 electron to contribute, and that's used in the bond. And carbon already has a full octet, so that's why we put it on the oxygen. So this is the Lewis structure, and this is actually just methanol. So let's see what the junior tutor said. First, calculate the total valence electrons, so they got 14. Now connect all the atoms with single covalent bonds to draw a skeletal structure. Given that the oxygen is bonded to 2 types of atoms, therefore connect oxygen to carbon and hydrogen. So there are a total of 5 bonds, each containing 2 electrons, so therefore 10 are consumed for making the skeletal structure. The remaining electrons are 4. So place the remaining 4 on the oxygen. Step 4, if the octets of all the atoms are not filled, then convert the lone pair on the most electronegative, but in our case, they're all filled. Calculate the formal charge. So this is an extra step just to double check to make sure we have the smallest amount of possible charges. So if we were to calculate the formal charge for all of the atoms, you end up getting 0 for all of them. And then the final Lewis structure is shown below. All the atoms in the molecule have a formal charge of 0, so formal charge is not shown. Yep. So this solution is correct. Okay, so those are all the questions for this session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And also you can leave a comment and give it a thumbs up if you enjoyed the video. And you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.